Okay, how many say that this is a balanced equation? 9, and how many say it's not balanced then? Should be about 8 of you. Well, we don't have 8 hands, but that's what the math should work out to be. It is balanced. Okay, let's go through what we did yesterday to determine this. Let me go ahead and write it again so I can get rid of this content and we can have a clean screen to work with. 6 carbon dioxides and 6 waters react to produce 1 glucose and 6 oxygen molecules. Okay. Okay, that doesn't look real great. I'll try to go to blue. If that doesn't work, I'll try to find a black one somewhere. So 6 carbon dioxide, 6 waters react to produce 1 glucose and 6 O2s. I look to the left-hand side of the equation to start with, and I read across, and I look for what different elements are involved in this reaction. Okay? The reactants, again, for those of you that missed yesterday, the reactants are going to be on the left-hand side of the arrow. That's where we start, and we read from left to right. So what we're basically saying is this many of this reacts with this many of this to produce this many of this, and if there's no number, it's an implied 1, and 6 of those. So what are the elements that we see? Because remember, our principle is that an atom, Dalton's theory of matter, and one of those principles is that the element or the atom is the smallest indivisible unit of matter. And we know that the atom is technically divisible. We can pull electrons off, we can change neutrons. But for our purposes here, the smallest block of matter we're going to have is going to be the atom. And so we don't lose any mass, we don't lose any atoms. All we do is reconfigure them. So the number of, we start reading from left to right, the first element we see is carbon. What's next? Oxygens and hydrogens. Any other elements? So it's a CHO. Again, I normally do CHO because you're going to see that over and over and over again, but in this case, it reads left to right: carbons, oxygens, and hydrogens. First, I'm going to be assessing the reactants. How many of each element do I have in the reactants? Well, for carbon, so look at the molecule. How many carbons are in a carbon dioxide molecule? How many carbons are in that molecule of CO2? In that molecule? 1. There's 1 carbon and 2 oxygens that make up a CO2 molecule. So carbon, I have 1 of them, but how many molecules do I have? I have 6 of them. So I have 6 molecules at 1 per molecule. Okay, 6 molecules at 1 per molecule. Do I have any other carbons on the reactant side? No. Next I go to oxygens. From left to right. Carbon dioxide. There's oxygen and carbon dioxide. As a matter of fact, for every molecule of carbon dioxide, how many oxygens are there? 2. And how many molecules do I have again? 6. So I have 6 molecules at 2 per molecule. Then continuing read from left to right as I come across, there's more oxygen over here, right? Water, H2O. Do the same principle. How many atoms of oxygen are in each water molecule? 1. But I have 6 molecules at 1 per molecule. Okay. Remember your rules of math, order of operations, it's going to be that plus that. Don't get your order of operations wrong. Okay? Any more hydrogen or any more oxygens? No. Next we look to hydrogens. Hydrogens only occur in the water molecule on the reactant side. Every water molecule has 2, and I have 6 molecules. So 6 times 2 for the hydrogens. So carbons, I have a total of 6. Oxygens, I have a total of 12 plus 6, which equals 18. And for hydrogens, I have a total of 12. So for this equation to be balanced, or excuse me, we're checking that it's balanced, but our first point is how many of each element do I have on the reactant side? On the product side, I have to have the exact same number of every single element. So we'll go to the products. Looking, again, it's kind of forming a matrix. Looking at carbons. On the product side, where does carbon show up? It's only in the glucose molecule. How many do we have? We have 6 per molecule, and we only have 1 molecule. So we have 1 times 6. 1 molecule at 6 per molecule. Oxygens. They're in both molecules, right? So it's going to be a 2-part again. Oxygen shows up 6 times in glucose, but there's only 1 molecule, so I've got 1 times 6. And then in the oxygen, it shows up 2 times, and I've got 6 of those. So 6 times 2. 6 molecules at 2 per molecule. And hydrogens. Shows up only in glucose, and I have 1 molecule at 12 per molecule. Okay? So the total number of carbons on the right, on the product side, is 6. Total number of oxygens is going to be 6 plus 12, which equals 18. And then hydrogens, 1 times 12 is equal to 12. Now I'm going to look at every one of the elements. Carbon, 6 and 6. The carbon's balanced. Oxygens, 18 and 18. The oxygen's balanced. Hydrogen, 12 and 12. The hydrogen's balanced. If every element is balanced, the equation is balanced. Okay? If every element is balanced, then the entire equation is balanced. And remember, what this equation is telling me is that if I take 6 carbon dioxide molecules and react it with 6 water molecules, I will produce 1 glucose molecule and 6 oxygen molecules every single time. This recipe doesn't change. This is my balanced form. What we're going to do next is work on taking unbalanced equations and balancing them. Okay? Because when you have an equation, it may be generally true. Yesterday we did this and I talked about if I said, first of all, if you combine carbon dioxide and water to produce glucose and oxygen, I don't really need those coefficients, right? It wouldn't be a true statement, but I'm just generally saying, hey, if I mix carbon dioxide and water, I can make glucose and oxygen. But I can't really use that to do much because I have to know the proportions. How do things mix? How do they mix together, and what do they produce, and what is the relationship between them? And we do get into stoichiometry. You're going to learn, for example, that if I know if I have a balanced equation, and I know how much carbon dioxide I put into it, I can figure out how much of everything I need and how much of everything I make, just from knowing one of them. Okay, so it becomes very, very important from here going forward that you understand what a balanced equation looks like and how to create one from a general equation. Part of our teaching yesterday also was that, okay, yeah, 6 molecules combined with 6 molecules to produce 1 molecule and 6 molecules. It's also true because these are proportions. It's a 6 to 6, basically a 1-to-1 relationship, right? But it's a 1-to-1, but for purposes here, let's say it's 6 to 6 produces a 1 to 6. The proportions by count is what we're dealing with, not by mass. I can say that 6 dozen carbon dioxides react with 6 dozen water to produce 1 dozen glucose and 6 dozen oxygen. I can say 6,000 carbon dioxides react with 6,000 water to produce 1,000 glucose and 6,000 oxygen. I cannot say 6 grams reacts with 6 grams to produce 1 gram and 6 grams. It's not by mass. It's by individual atom count. Because frankly, the molecules don't care how massive the elements are that make up the molecule. What they care about, remember valence shell bonding? What they care about is how many of them do I get? not how much do they weigh, which is not technically what we're talking about with mass, right? But one way to think of it. They don't care how massive, how much stuff is in that atom. What they care about is how do our valence shell electrons match up? And so I need a certain number of you, not a certain mass of you. Okay? So that's significant. And we also talked about Avogadro's number yesterday, which is really part of one of the future modules. But remember, this principle of 6 individual plus 6 individual produces 1 individual and 6 individuals, okay, can be extended to greater and greater numbers of count. So we talk about individuals, we talk about pairs, we talk about dozens and baker dozens and scores and reams and all these different units of count. We have this unit of count in chemistry called a mole. And we'll go into more detail about that. Yeah, it's cute, it's funny, but mole is a number which is 6.02 times 10 to the 23rd of them. And yesterday I finished the lecture by saying that when you have a mole's worth, you actually have enough that you can do something with. I said if I had 2 or 3 sodium chloride molecules in my hand, I probably do and don't even know it, you know? They're so small. Who's to say I don't have any? But if I get a large number of them together, so many of them that I can actually see it, I start to see a salt crystal in my hand. That is millions, if not trillions, of molecules. Okay? To have enough that I can actually do something with it, that I actually can take it out and measure it out in some way, that I can actually use it in computations. I need many, 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 many of them before I can start to see them, let alone use them effectively. And the unit we use is a mole. In the future, when I say I have 1 mole of sodium chloride in my hand, what I'm actually saying is I have 6.02 times 10 to the 23rd individual molecules of sodium chloride in my hand. And that is a huge number. Is it going to be perfect? No. But the scale is so huge. 6, and then 602, and then 21 zeros after that. That is a massive, massive number. And that's how many we need so we can start to see them and deal with them and work with them and measure them and do these kind of reactions predictively. Okay? So that's kind of where we were yesterday, where we ended yesterday. We're going to pick up with some of the other examples on page 228. If you look on 228, this problem was example 6.2, the second problem in the example. Okay? So if you still don't understand this problem in particular, look to page 228 and 229, and it goes over this very problem. Let's go ahead and look at the first one on that page. Example 6.2 on page 228. We need to get a little bit familiar with seeing the phase symbols as well. This one has an aqueous in it. Do you remember what aqueous means? In water. So aqueous means in water. So we've got solid, liquid, gas, and aqueous. It says 2 hydrochloric acids, 2 HCl aqueous. Now I just told you HCl is hydrochloric acid, right? You may or may not have known that that's hydrochloric acid. Why would you tend to find HCl aqueous? Think about it. Do you have any hydrochloric acid? Yes, sir. Sure. Actually, Emily, could you hand him the box of tissues from there? Thank you, ma'am. And just hand it back when you're done. So we got hydrochloric acid. If we had pure hydrochloric acid, do you agree that that would be very caustic, very dangerous? If you had pure acid? So when I say I've got HCl aqueous, virtually every time you deal with hydrochloric acid, it's going to be aqueous. Because what have I done? I've diluted it with water. I've taken a pure acid, which you want to make sure that the container you put it in can hold it because it'll burn through a lot of things. And we basically add water to it to dilute it out. To the point where a lot of us may take medications that have hydrochloric acid in them. I mean, at certain concentrations, they're caustic and they're deadly. At other concentrations, they're medicinal, and we use them. You'll see later that the stomach acid we have, you know, when you are ill and maybe you chew your cud, you know what I'm talking about? Comes up and goes back down. That burn you feel is hydrochloric acid. Burning your esophagus because your esophagus isn't designed for that acid. Your stomach is. Your throat is not. That's why it burns. Your esophagus is being burned by acid when that happens from your stomach. Your body makes hydrochloric acid. Okay? So 2 hydrochloric acid aqueous and 1 calcium bromide. Not calcium dibromide, right? Because it's ionic. 2 hydrochloric acid and 1 calcium bromide react to produce, that's aqueous and solid, okay? React to produce 2 hydrobromic acid, that's probably aqueous, right? Aqueous and 2 calcium chloride solids. Okay. Copy that right? All right. Yep. So the question again is whether or not this is balanced. Whether or not this is balanced. Process, I'm going to look from left to right. I find hydrogen, chlorine, calcium, and bromine. Hydrogen, chlorine, calcium, bromide, right? I'm gonna shorten my matrix just to kind of get it in working order over here. So hydrogen, chlorine, calcium, bromide. I'm going to see my reactants and my products. These columns I have to match across. So looking at hydrogen from left to right, how many hydrogens do I have in reactants? I have 2 sets of 1, which equals 2, right? Here's the deal. Each one of these elements only occurs once. Do you see that? Okay, they only occur once. So once I count them up in one molecule, I'm done with that element on this side. We can also look at the other side and see the same thing. Hydrogen, bromine, calcium chloride. Okay, when I get to the other side, I don't have to account for multiple occurrences of the same element. They're only showing up one place. So it makes it kind of quick for me. So hydrogen, 2 sets of 1. Chlorine, 2 sets of 1, right? Okay. Calcium. Say it with me. How many? 1 set of calcium. Yes. Thank you. Calcium is 1 set of 1, and bromine 1 set of 2. So if you think this way, sets of how many? Your math always set it up. Sets of how many? 2 sets of 1, 2 sets of 1, 1 set of 1, 1 set of 2. Any problems with seeing those numbers from the equation? Okay, go to the product side. Hydrogen. I've got 2 sets of 1 right here. Chlorine. 2 sets of 2. We're done. We don't have to do any more. Because the question was what? Is it balanced? No, I'm done. This one is unbalanced, so it doesn't matter what the other ones are. It can't be balanced. Now, if I went through and did the rest of them just for process, I would say calcium would be 2 times 1, and bromine would be 2 times 1, which equals 2. And I would go through and say hydrogen's balanced, chlorine's not balanced, calcium is not balanced, bromine is balanced. They're not all balanced, therefore it's not balanced. Now, actually I was going to go to the next step, which would be, okay, it's not balanced. Balance it. Because that's the way the questions on the module exam are going to go. You're going to very seldom you're going to see, is it balanced or not? It's going to say, is it balanced? And if it's not balanced, you balance it. And that's the final step in this process for this module. Determining whether or not a chemical equation is balanced, and if it's not balanced, then going ahead and balancing it. Does anyone want to work, and feel free, again, you got to get over your embarrassment. Does anybody want to, not that you should be embarrassed, you should not be. Does anyone want to work another one to find out if they're balanced or not? Or does this concept, is pretty straightforward, that you have it? Because we'll move on to, okay, if it's not balanced, how do we balance it? So we're still going to have to do this, the next few problems. So you'll have a few more examples if you just want to see a few more examples. But if you really need work on it, we'll do another one that just focuses on this. Nope. Yes, sir. Okay. Yeah, 2, and then it has the molecule after that. Mm-hmm. We had 2 calcium chlorides over there, for example. That was one of the molecules that were up there. Mm-hmm. 4, yeah. There were 2 sets of 2. That's for the chlorine. Okay? For the calcium, it would be 2 sets of 1. Because 1s aren't there, it's an implied 1. So I have 2 sets of 1 calciums and 2 sets of 2 chlorines. Okay. And the thing about balancing equations, which we're getting into right now, and I mentioned it yesterday, is that you do have the authority in balancing an equation to change the coefficient. This number right here. You as a student, I as a person, we as people, we can go through and change the coefficients, the numbers in front of the whole molecule. What we cannot do, which is the common mistake of students, is to start toying with the subscripts. You can't do that. If you need 1 more chlorine, and you decide, hey, the way I'm going to get that chlorine is I'm now going to make it a CaCl3 molecule. Do you realize you've just jacked up all of valence shell electrons? You've just thrown away all of Vesper theory. You have decided on your own that everything we've learned over the last 3 modules doesn't really apply to you. You don't have that authority. You can't do that. You can't decide that, yeah, this is going to be a covalent molecule even though I know it's supposed to be ionic. You don't have that authority. You can say, give me 2 of them. Give me 3 of them. You may think of it as God has given us the storehouse of all the different molecules we can make, and he gives you the option to pick how many of them you want. But you can't go in and make up your own. Okay? I mean, that's maybe a little dramatic, but that's true. And some of you will do this. You'll do it repeatedly. Will, if you need to stand up, then stand up. Okay? So you can change the coefficients, but you cannot change the subscripts. Now, this is different than me asking you, hey, what is the formula for calcium chloride? When you start working with calcium chloride and you say calcium, okay, calcium's a column 2 element, so it wants to go 2 positive. Chlorine is a column 7, so it wants to become a 1 negative. And so I do this deal here, and I come up with CaCl2. This isn't you deciding it has 2. This is you discovering what God has already ordered it to be. What I'm saying is you can say, I don't need 1 calcium chlorides, I need 2 calcium chlorides. That's fine. What you cannot do is say, you know what, I decided it's going to be a Cl2 or Ca2Cl3 molecule because I need 1 more calcium and 1 more chlorine. Never mess with the subscripts. Was that adamant enough? I'll just say, you're playing God. Sorry, don't have the authority. I mean, you know how powerful I am, and I don't even have that authority, okay? So if I don't have that authority, you definitely don't have that authority. That was meant to be a joke. You got to keep up with me. Come on. Balancing chemical equations. We are on 229. The examples they give us. First example on 229, again, I'll do it on the board. That way you have the example in your book. If you don't get it from the board, you can review it again. It says to balance, and for right now, I'm going to drop the phase symbols, okay? Technically, the phase symbols, they provide us additional information. For balancing them, they're not always necessary. So just for shortcut for me as I write them on the board, I'm going to drop the phase symbols. You've got N2 and H2. react to produce NH3. So help me out here. Nitrogen, gas, homonuclear diatomic. We're not going to find nitrogen alone, only N2s. Hydrogen, homonuclear diatomic, again, H2s, produces, what's the name of that molecule? Okay. You might have seen its close cousin, which was, what is the only positive polyatomic ion we have? Ammonium. So this is ammonia. Okay. NH3, which is a pyramidal, right? Based on a tetrahedron, but nitrogen has an unbonded pair, so it pushes them all down for bond angles of 107 degrees. Right. Sorry, I'm reviewing all that old easy stuff, but keep it fresh, right? So nitrogen, hydrogen produces ammonia. How many do we have? Let's make our matrix. Nitrogens and hydrogens. Anything else? Nope. Reactants, products. What do they look like? Nitrogen, I've got one set of 2. Hydrogens, I've got one set of 2. The right-hand side, one set of 1 and one set of 3. Now remember, we can only mess with coefficients, not subscripts. So I look into this and I say, what do I need more of? That's my technique. What do I need more of? Look at the specific element. What element do I need more of? I need more nitrogen in the product side. I need more hydrogen on the reactant side, right? Now this is pretty straightforward. This is an easy, very easy equation, but because it's the first one, baby steps in the book. I need more nitrogen on the right. I need more hydrogen on the left. So let's do that. Somebody pick one. Nitrogen. You want to add nitrogen to what side? To the right. How are we going to do that? Add a coefficient. Make it what? Let's just baby step it up. Let's make it 2. Okay, so this becomes now 2 times 1, which is 2, and 2 times 3, which is 6. Okay? What do I need more of? I need more hydrogens, right? Let's do the process. Let's walk the process. What do I need more of? I need more hydrogens on the reaction side, the reactant side. How many do I need? I need a total of 6. How do I build it up? I build it up in sets of 2. How many sets of 2 do I need in order to have 6? 1, 2, 3. 1, 2, 3, right? 3. Entschuldigung zu mir? I said, I joined him in counting in Spanish, and then I counted up in German. And then you said something, and I said, you said Jap? That's what I thought you said. And that's why I replied in German, excuse me? Ja, ich kann Deutsch sprechen. Ich weiß nicht alles, aber ich kann ein bisschen. I don't know if I can't speak at all. I haven't taken it since my sophomore year in high school. But I took 2 years in high school, and then I went to Germany for 3 months. And I came back, and I validated 2 years of high school, and then I validated 2 years of college. But I haven't spoken it with a German speaker since 1980. I can read Greek. I can read a little bit of Hebrew. I can speak a little bit of Japanese, Arabic. No, not real fast. Japanese is probably my worst. I was only in Japan for 6 months or 7 months. But those are the weakest ones because the least amount of exposure. I was in Germany for 3 months, but I was culturally immersed in Germany. I didn't have anybody. People there wanted me to teach them English, and I eventually had to stop speaking English so they would speak to me in German so I could learn German. But after a couple months in German, I came home, and then I had difficulty thinking in English. I was thinking in German, which is really a weird experience when you, hopefully you all eventually get to have that experience, to be culturally immersed, and then to realize how much of your language dictates how much you understand, because we take ideas and we construct them into symbols, which are words, and we put those words in different orders to try to communicate meaning. And when you start thinking in another language, your thoughts change. It's really bizarre. It's so existential, you know. It is. Actually, I think I referred to it earlier. I was talking to Mr. Parker about this. The movie that's out right now, Arrival. I teased you guys yesterday saying it was a cerebral sci-fi movie, but don't worry, none of you would get it. I was kind of that was a joke too, but you had to know what I was saying in order to understand the joke, which is kind of what the movie's about. The movie is about language. The main actor in this movie, Amy Adams, she is a linguist, and she gets called in to help when aliens land on Earth, because they're obviously trying to communicate to us, but we can't understand what they're trying to say, so they bring in a linguist to try to help understand what they're saying, because they're speaking their language, which is, you know, obviously very alien, because they are aliens. And the whole premise of the movie is, as you come to understand how other people put their thoughts together, you begin to think differently. Is anybody going to go see the movie? Spoiler alert, because I can tell you it's really cool. I'll go see it again. It's really good. But ultimately, in the end, what the aliens bring is they bring a gift, and what the gift they bring is their language. Wow. Because their language is organized around time, and in the way it's organized, it allows the person who becomes fluent in it to see forward in time. So it's kind of like in your mind kind of a thing. And throughout the movie, they're showing flashbacks, but you think they're flashbacks, but in the end, you come to understand that they're really flash forwards. Boom. Do I believe in aliens? Do I believe? Do I know that they do or do not exist? No.
Do you think they could?
Based on carbon or silicon? Write the balanced equation for the following. C3H8, let's do a few of these so you get the process down. C3H8 plus O2 reacts to produce CO2 and H2O. Again, look for this pattern. I'm producing carbon dioxide and water. What am I doing? I'm combusting something. What does combustion require? Oxygen. What am I burning? A carbon, hydrogen, oxygen chain. This is actually a C3H8O0. Okay? That's the way I look at it. That's an O0. But a carbon, hydrogen, oxygen chain burns in oxygen to produce carbon dioxide and water. You're going to see it over and over and over and over again. In fact, if I just put up there, produces carbon dioxide and water, what would you tell me? It's got to have oxygen. Okay? And what's underneath here? Some carbon, hydrogen, oxygen chain fuel. Boom, there you go. Now, is it balanced? Looking from left to right. Talk me through it. What do I see? So give me the elements first. Oxygen, and then carbon, oxygen, hydrogen. Am I accounting for all the elements? Is every element that's on that equation on the left side of my matrix? Okay, I agree. Because carbon, hydrogen, oxygen chains burning in oxygen produce carbon, hydrogen, and oxygen. All right, so I'm set my matrix with my reactants and my products. Okay, for carbon, all together. One set of three. Good, that's how we're going to do it. Okay, one set of three. Hydrogens, one set of 8. And oxygens, one set of 2 produces 2. Yep, thank you. So one of 3, one of 8, and one of 2. Product side, carbons. One set of 1. Okay. Hydrogens. One set of 2. And oxygens. One set of 2 and one set of 1. Okay. Everybody feel comfortable in process to get this far? Is it balanced? 2 and 3, no. 8 and 2, no. 3 and 1, no. None of them are balanced. So no, it's obviously not balanced as an equation because none of the individual atoms or none of the individual elements are balanced. Process now. Where do I need more of something? Okay, here's the first chance I get to teach you a hint. Look in the equation and look for elements that are in their elemental form. Do you see something that's in its elemental form? What up here is the way it appears naturally as an element? Oxygen appears naturally in its elemental form as an oxygen molecule, right? So basically what I have here is this chain plus oxygen. This is my elemental form. What I mean elemental form, if it's a homonuclear diatomic, it's going to be a molecule. But if it's not a homonuclear diatomic, it's going to be all by itself. Like plus calcium, plus sodium, plus whatever. So I look for something that's in its elemental form. I'm going to hold that. I'm not going to mess with that until the very end. Because what this means is if I ever adjust the oxygen here, I don't mess anything else up. You'll see the value of that in a minute. Save the elementals for the last. So carbon, hydrogen, oxygen. I'm saving oxygen for the end. Look at these two. Which do I need more of? And where? Okay. Carbons. Carbons. I need more carbon on the product side. To get more carbon on the product side, what am I going to do? Put 3 in front of the carbon dioxide, right? Now that's going to mess up my carbon and my oxygen count, right? I go to carbon now. I now have 3 sets of 1 carbon to give me 3. But I also now have for oxygen over here, right here, it's now 3 sets of 2, which changes this to 6. And now I have 7. Right? Okay. But my carbon's balanced. And you're going to see where this is kind of like a puzzle back and forth because when you change a coefficient, you mess up the counts of every element that's in that coefficient. Or excuse me, when you add a coefficient or change a coefficient, you mess up the count of every element that's in that molecule. So there's some strategies to use. As long as you keep doing legitimate steps, you'll end up with the right answer. But there are quicker ways, better ways to do it than others. So we've balanced the carbon. What do we need to balance now? Hydrogens. We have 8. We need 8. How are we going to produce 8? Put a 4 in front. Now that's going to give me my 4 sets of 2, which gives me 8. But it also messes with what? Down here in oxygen. And now I have 4 sets of 1, right? Which is 4. So now total I have 10. Do you see how when you change a coefficient, it messes with the count of every atom, every element that's in that molecule. But I've got balanced carbon, balanced hydrogen, but now I'm left with oxygen. Right? And here's why I said save the element for last. Because no matter what I put in front of that oxygen, it doesn't mess with the atom count of anything else. It only changes the oxygen count. So I can look at this now and say, I need 10, and I'm building it in sets of 2. Give me 5 sets of 2. Nothing else gets messed with. That gives me 10. All 3 are balanced. Now my equation is balanced. Okay. Now I can look at this and say, okay, if I take 1 molecule and combust it with 5 molecules of O2, I produce 3 molecules of carbon dioxide and 4 molecules of water. Every time, because this is my balanced equation. And we're driving to get balanced equations. So yeah, you need to figure out if it's balanced or not, but that leads you to the immediate next step. Okay, if it's not, then what is it balanced? Balance it. Now that right there is the last example in the module. So we have technically finished module 6. Let's see, time-wise, what, 2 minutes? let's at least start. When the bell rings, we'll stop. Tomorrow, probably be a lookalike quiz from one of the problems at the end of the module, one of the on your owns. Probably. Nope, it's yours. And again, tomorrow I could collect it and grade it. You're not going to know each day whether it's going to count or not. Don't get frustrated if I don't collect it, because the reason I had you take it was pre-learning. That even if you got it wrong when we went over the answer, you're able to learn from it. If you got it right, you know you got it right. If you got it wrong, you know you need to learn, and so you paid better attention. One of the shortcomings would be if you think you've got it and you get the right answer, you don't pay attention, and you got the answer for the wrong reasons. Okay? So for those of you that may get the right answer but for the wrong reasons, you still need to listen up. Okay. Sometimes you can make an error in your thinking and it travels for a long time before it gets corrected, and then by the time you ever get called on it, you've got so much learning that's based on that wrong information that it's hard to unlearn it. Okay. Hydrogen and oxygen can react together violently to make water. Write a balanced equation for the reaction. It's a violent reaction to make water. Okay, I've got hydrogens, oxygens. Left-hand side, I've got one set of two. Oxygens, I've got one set of two. Product side, hydrogens, I've got one set of two and one set of one, which equals 1. So 2, 2, 2, and 1. Okay? So what do I have too little of? Well, hydrogen's already balanced, right? So oxygen, I need more on the right. I'll make that a 2. 2 sets of 1 become, or excuse me, yeah, 2 sets of 1 becomes 2, but it messes with my hydrogen. My 2 sets of 2 become 4. Now what do I need more of? Hydrogen on the reactant side, I need 4, so I need 2 sets of 2. So writing the reaction, you would have had to have known, it says hydrogen and oxygen combine to react to produce water. You would have to been savvy enough to say, it's not simply H, it's H2. It's not simply O, it's O2 to produce H2O. But that is 2H2 plus O2 is 2H2O is the balanced equation.